Welcome to my presentation on feasibility of satellite rainfall estimates for the Zambezi Basin. As you can see, my name is Webster Gumindoga from Zimbabwe, Department of Construction and Civil Engineering. So I'll go straight into my presentation, where the outline is on the Zambezi Basin, satellite-based rainfall estimation, findings on performance, findings on bias correction, findings on error propagation through hydrologic evaluation, and recommendations for future work. I would really say, ladies and gentlemen, that it's very important to observe our research catchments from space. For example, in the Zambezi Basin, which is the most prominent river basin in Southern Africa. Quantitative estimates of water balance components in this important basin are limited. So remote sensing technology, including satellite rainfall estimates, offers opportunities to integrate remote sensing data into hydrological models. And the products, however, only are representations of reality with the specific spatial, that is pixel footprint, and temporal resolutions when you speak about the revisit time. So research on effects of satellite rainfall errors propagate to effect streamflow simulation and mismatch are actually needed for us to be so much knowledgeable and to trust satellite rainfall estimates. So came up with 4 objectives that I'm going to share with you. So first one was to carry out performance evaluation of a rainfall product called the CMOF, which is a satellite precipitation product in the Zambezi Basin. And then I evaluated the performance of 5 bias correction schemes for CMOF rainfall estimates in the basin. And then to perform a hydrologic evaluation of bias corrected CMOF rainfall estimates at the headwater catchment of the Zambezi River, and to assess propagation of CMOF rainfall errors to real stream flow simulation and mismatch in a headwater catchment of the Zambezi Basin. So in terms of data availability, as you know, that CMOF rainfall images are quite available from 1998, but because of the limitations of the in situ weather gauges, we downloaded from 1998 to 2013 with 66 stations, and streamflow measurements were on the Watopa gauge in the upper Zambezi Basin. Also downloaded shuttle radar terrain mission, 30-meter GM from the Earth Explorer USGS, downloaded land use and soil grids, and also calibrated a representative elementary watershed raw runoff model. And so in terms of performance of CMOF satellite rainfall product in the Zambezi Basin, we use detection statistics such as probability of detection. We use bias decomposition, heat bias, missed rainfall bias, and false rainfall bias. And you see a lot of statistics that are used to calculate this so that we come up with a conclusion on whether these rainfall estimates are very important. And performance evaluation of CMOF on the key findings are that, as you can see, the spatial distribution of the errors in some areas is very low, in some areas is very high, or it's positive and negative, representing estimations and overestimations. But key to notice that there's wrong detection of rainfall occurrence is prevalent in dry season. Correction now of satellite rainfall estimates advocated for heavy rainfall events, and there are also high false bias. Errors in CMOF rainfall should be corrected before the product can serve applications, such as in hydrological modeling. And you can actually see that we went on to do correction based on the results in performance assessment. We developed 5 bias correction factors, but I'll just emphasize on the 2, which is one of them is called the spatial temporal bias, which corrects for the spatial and temporal errors in the satellite rainfall, and one because of the topology of the Zambezi Basin, one which is called the election zone bias correction. And so the formulas are as given there. But the principle of bias correction is that only we calculate bias only when a minimum of 5 rain days were recorded within the preceding 7-day window with a minimum rainfall accumulation depth of 5 millimeters. Otherwise, a value of 1 applies as bias correction factor. And so the following The following graphs show performance of bias correction schemes, and we can see that the temporal aspects of satellite rainfall estimates bias are more important than the spatial aspect of bias, as you can see with the various performance of the bias correction schemes. And also, we looked at the on the fact on whether elevation and distance, large scale water bodies which are prevalent in the basin, whether this affects SIM of performance. And so we saw that SIM of performance increases for higher elevation, like greater than 950 meters. The Taylor diagram shows us that SIM of estimates improved at increasing distance, less than 10 kilometer, to large scale water bodies. And then lastly, we looked at on where the hydraulic evaluation of bias corrected SIM of estimates, um, in terms of how can we actually use a rainfall runoff model to to further assess the performance of satellite rainfall estimates. So in this sense, we calibrated a representative elementary watershed model known as RAW, right, by use of rain gauge rainfall, which serves as a benchmark to the simulation results. The model was recalibrated when bias corrected and uncorrected rainfall replaced rain gauge based inputs as rainfall forcing. So you can actually see from this graph in terms of the relative bias that the rule runoff model translates small rainfall errors to large stream flow errors, and the magnitude of error amplifications smaller for bias corrected satellite data. And we also saw that the optimized rule parameter values changed by greater than 50% when gauge based rainfall inputs are replaced by uncorrected SIM of estimates. All right. And so, in terms of conclusion, we saw that SREs or certain rainfall estimates contain errors that manifest in spatial and temporal domain. Um, so the spatial temporal bias is effective in removing bias, and bias correction is critical, can yield to substantial improvement in capturing both stream flow pattern and magnitude for effective water resource management. And the new hydrological insights on the propagation effects of satellite-based rainfall errors in stream flow modeling are realized. So we recommend extensive experimental observational networks, multi-satellite blended precipitation products, combining multi-objective functions into one scalar composite or weighted objective function. So I leave you to enjoy the pictures of the Zambezi Basin and to acknowledge the University of Twende that supported this research, and also WaterNet, University of Zimbabwe, and I thank you.